Today we will start off with testing of hypothesis, different notions and concepts. If you can recall, in our early lectures we spoke about the theory of statistical inference, which has got mainly two parts, estimation and testing of hypothesis. So today we will dive deep into the testing of hypothesis. We have seen that here the inquirer starts with some tentative idea regarding the unknown population, and on the basis of the sample observations, we try to know or try to judge how tenable this idea is. This tentative idea is called a hypothesis, and the process of judging its validity is known as a test of the hypothesis. So what is a hypothesis? It is a tentative idea regarding a probability distribution or regarding an unknown parameter of a probability distribution. This tentative idea is called a hypothesis. Now, what do we mean by the phrase tentative? Here, by tentative assertion, we mean that the assertion has to be verified on the basis of the sample observations. The verification of any statistical hypothesis on the basis of a set of sample observations is known as a test of the hypothesis. Here the sample observations are very important because we have already seen in several occasions that we cannot enumerate the whole population. So to verify whether a hypothesis is correct or not, or whether a tentative idea is justifiable or not, we have to depend on the sample observations. Now we will classify different types of hypothesis. First, simple hypothesis. A hypothesis that specifies a population or equivalently a probability distribution completely is called a simple hypothesis. Now what do we mean by specification in a complete sense? That means the population parameters will all be specified by a simple hypothesis. On the other hand, if we talk about a composite hypothesis, it is such a hypothesis that fails to specify a population or equivalently a probability distribution completely. That means it does not pinpoint the parameters of a probability distribution or equivalently a population. Let us see this through a set of examples. We consider a normal population with mean mu and variance sigma square. Now on your screen you can see H1 mu equals to 0, sigma equals to 1. This is a hypothesis. H1 is a hypothesis. Now you see, for a normal distribution, if we specify the value of mu and the value of sigma or sigma square, then the population is completely specified. In this sense, H1 is a simple hypothesis. Similarly, we can have mu equals to 3 and sigma equals to 2. This is also a simple hypothesis. Now if we go to H3, which is specifying mu equals to 0, but it does not speak anything about sigma. That means the normal distribution or the normal population is not completely specified. So here obviously H3 will be a composite hypothesis. Similarly, you see in H4 the value of sigma is specified, not of mu. In H5 we are saying mu is greater than 0, sigma equals to 1. So here mu is greater than 0, so it does not specify the value of mu. It just says that mu is positive, but you can take several values. So again, this hypothesis fails to specify the population completely. And look at the last example. Mu equals to 0, sigma not equal to 1. The value of mu is specified, but the value of sigma is not specified. It is only saying that sigma is not equal to 1. With this information, obviously, we won't be able to write down the probability distribution, and also because of that, we won't be able to find out the probabilities. So in this sense, these are composite hypotheses. Now we come to the two most important types of hypothesis in testing of hypothesis. Null hypothesis. The hypothesis which is set up and whose validity is tested against possible alternatives is called a null hypothesis. So this is the main hypothesis that we are going to test, and we will be concerned with rejection or acceptance of the null hypothesis only. On the other hand, an alternative hypothesis is that which contradicts the null hypothesis. That means in case of testing of hypothesis, we have a null hypothesis that we will test, and we have an alternative hypothesis which will contradict the null hypothesis. So if the null hypothesis is accepted, obviously on the basis of sample observations, then the alternative will be rejected and vice versa. We take an example. Suppose P is the probability of getting head in a single toss of a coin. Suppose our problem is to test H0 P equals to half against H1 P not equal to half. In general, we denote a null hypothesis by H0, H suffix 0, and an alternative hypothesis by H1, H2, H3, etc. So here H0 is the null hypothesis, P equals to half. Now look at H1, P not equal to half. That means H1 is contradicting H0. So in this sense, it is the alternative hypothesis. Now, on the basis of the sample observations, if we accept H0, then automatically H1 will be rejected, and if we reject H0, then automatically H1 will be accepted. So I again stress upon the fact that we will test the null hypothesis only. We will not test the alternative hypothesis. Test statistic. We have defined statistic earlier. What is a statistic? Any statistical measure based on the sample observations. So test statistic in particular is a statistic that is used for testing the hypothesis. So you can see on your slide, the statistic which is used to test a null hypothesis is called a test statistic. We can take an example. We go back to the same example of testing P equals to half against P not equal to half. So we need a sample. So we toss the coin a number of times, say 10 times, and let X be the number of heads obtained in these 10 tosses. Then can you tell us that what can be used as the test statistic? So in this experiment, obviously our statistical measure based on the sample values will be the test statistic. So if X be the number of heads obtained in 10 tosses, then X itself can be used as the test statistic. Or equivalently, to compare it with P, that is the population proportion, we can use the sample proportion as the test statistic. So what will be the sample proportion in this situation? X by 10, number of heads divided by the number of tosses. So that can be used as the test statistic. We generally denote a test statistic by capital T. That we will use this notation for now on. Now, critical region. Fine. We will use a set of sample observations to test a null hypothesis. That is, to take a decision whether to accept or reject a null hypothesis. Now the question is, for what value of this statistic or the test statistic we will accept the null hypothesis, and for what value we will reject the null hypothesis. The set of values of the test statistic for which we reject a null hypothesis is known as the critical region of the test. Actually, you see, when we perform a test, we have a test statistic. Now, all possible values of the test statistic is known as the sample space of the test statistic, and in general, it is denoted by script X. How script X is written? That is there on your slide. Now, this sample space may be divided into two mutually exclusive and exhaustive subsets. One is called W and the other one is called W complement. These two are made in such a way that if the value of the test statistic belongs to W, we reject H0, and if it belongs to W complement, we accept H0. W and W complement are respectively known as the critical region and the acceptance region of the test. Now in our present problem, that is, we want to test P is equal to half against P not equal to half, and we toss the coin 10 times for this purpose. Now suppose we decide to reject H0 if the number of heads obtained out of 10 tosses is less than 2 or more than 7. So what are the all possible values of X? You are tossing the coin 10 times and X is the number of heads obtained. So X can take up any value from 0, 1 to up to 10. So this set containing 0, 1 to up to 10, this will be the sample space of the test, or the sample space of the test statistic, which will be denoted by script X. Now we have decided to reject H0 if the number of heads obtained is less than 2 or more than 7. So for which values of X we are rejecting H0? For 0, 1 and then 8, 9, 10. The set consisting of these values will be called the critical region, and we denote it by W. Now the question arises, then for which values we are going to accept the null hypothesis? Obviously for the values 2, 3, 4, 5, 6 and 7. A set consisting of these values will be the acceptance region, and we will denote it by W complement. Now the question is, we will decide whether a null hypothesis is true or false on the basis of a set of sample observations. Now, isn't it possible in the present example that even if the coin is unbiased, we can have 10 heads out of 10 tosses? It is possible. So, you see, even when we are rejecting the null hypothesis, the coin may be truly unbiased. That means there is a chance of committing error. Similarly, suppose the coin is truly biased, but even then out of 10 tosses, we can get 5 hits. So that means even when the coin is biased, on the basis of the sample observations, we are accepting H0. So again, there is a possibility of committing an error. So there are two possible types of errors that one may commit in any testing problem. Since the decision of accepting or rejecting a null hypothesis is made only on the basis of a set of sample observations, so we may commit an error in making the decision. In any testing problem, as I mentioned, we can commit two types of error: rejecting a null hypothesis when it is actually true, and accepting a null hypothesis when it is actually false. Now, rejecting a null hypothesis when it is actually true is known as the type 1 error, while accepting a null hypothesis when it is actually false is known as type 2 error. So, in any testing problem, we may commit these two types of errors. On your screen, you can see there is an error table. There are 4 different situations that may arise in any testing problem. You can see the true state is H0 is true, or the true state may be H0 is false. But we can take two types of decisions on the basis of the set of sample observations: accept H0 or reject H0. When H0 is true, that is when the true state is H0 is true and we are accepting H0, we obviously take a correct decision. When H0 is true and we reject H0, then we commit type 1 error. When H0 is false, that is the true state is H0 is false, and we accept H0, that means we commit an error which is called type 2 error. On the other hand, when H0 is false and we reject H0 on the basis of sample observations, again we take a correct decision. So these 4 situations may arise in a testing problem, which can be summarized by this error table. Now my question is, while performing a test, will you be able to say whether you have taken a correct decision or you have committed an error? And if committed an error, what kind of error you have committed? So we have a very important note regarding these errors. Since the true value of the parameter remains unknown, it is not possible to say whether an error has been committed or we have taken a correct decision. What we can find out are nothing but the probabilities of these errors as well as the probabilities of taking correct decisions. In particular, we have probability of type 1 error. As we already know, it is the probability of rejecting H0 when H0 is true. So in notational form, it is probability that T will belong to W given H0, that is H0 is true. On the other hand, probability of type 2 error will be the probability of accepting H0 when it is false. Now, when we accept H0, when T belongs to W complement, so it is the probability that T will belong to W complement given H1. Level of significance. This is very important in the context of testing of hypothesis. Now see, obviously we will try to make a test in such a manner that which we can reduce the probabilities of both the types of errors. To be specific, we can minimize the probabilities of both the types of errors. But it can be theoretically shown that in tests with fixed sample size, if we try to minimize the probability of one kind of error, that will result in the maximization of the other kind of error. That means theoretically it can be shown that we cannot minimize the probabilities of both the types of error simultaneously. So what to do? In this situation, we put an upper bound to the probability of type 1 error beyond which we do not allow it to increase. Under this restriction, under this constraint, now we try to minimize the probability of type 2 error as far as possible. That means we first safeguard against the probability of type 1 error, and then on the basis of that safeguard, we try to minimize the probability of type 2 error as far as possible. This upper bound to the probability of type 1 error is known as the level of significance of the test. Normally, we denote a level of significance of a test by alpha, and the common values of alpha are 0.05 and 0.01. When alpha is 0.05, we are said to conduct a 5% test. On the other hand, when alpha is 0.01, we are said to conduct a 1% test. Now, a natural question may arise, why we are safeguarding against type 1 error? Why not type 2 error? We could have done the reverse way. That means we could have put an upper bound to the probability of type 2 error. And under this restriction, we could have tried to minimize the probability of type 1 error as far as possible. But we do not do that. Why? I can give you a very classical example. Suppose a person is taken to a court in a case of murder. Now, if the murder is proved, the person will be hanged. And if the murder is not proved, the person will be freed. Now, normally in courts, when a person is taken to the court, he is assumed to be non-guilty, innocent. So here, the testing problem is H0, the null hypothesis, the person is innocent, H1, the person is guilty. Now, suppose you are the person. Think yourself as a person, then only you will be able to appreciate this example. Now see, what is type 1 error? The person is innocent and the person is declared to be guilty, so he will be hanged. That means an innocent person will be hanged. On the other hand, what is type 2 error? Accepting H0 when H0 is false. That means you are declaring the person to be innocent when he is actually guilty. Now, if you are the person, which is more fatal? Which error is more fatal? Obviously type 1 error. An innocent person cannot be put to death. So that is why we safeguard against type 1 error. Size. As I mentioned that the type 1 error is the upper bound, or to be specific, the level of significance is the upper bound to the probability of type 1 error. So what is the actual probability of type 1 error? That is called the size of the test. So obviously size will be less than or equal to the level of significance of the test. Power. The power is probability of rejecting a null hypothesis when it is actually false. So power will be the probability that T belongs to W, the critical region, given H1. That is, T belongs to the critical region given the alternative hypothesis, when the alternative hypothesis is true. So this can be written as 1 minus probability T belongs to W complement given H1. That means 1 minus probability of type 2 error. Recall that T belongs to W complement given H1 is what? T belongs to the acceptance region given the null hypothesis is false. That is type 2 error. So power can be written as 1 minus probability of type 2 error. Now we come to two important things, one-sided test and two-sided test. What is a one-sided test? We consider the following testing problems. Theta equals to theta naught, that is H naught, against H1 theta greater than theta naught. Now, theta is a parameter and theta naught is some specified value of theta. Alternatively, we can also think of theta equals to theta naught against theta less than theta naught. Can you tell me why are these called one-sided tests? Now, these are called one-sided tests because you look at the alternative. We are taking either theta greater than theta naught or theta less than theta naught. So in these testing problems, we are trying to verify whether a test statistic T assumes a significant value on one side or one tail of its distribution. Such tests are known as one-sided tests or one-tailed tests. If you look at the diagram, you can see that we are looking only at one side of the test, one side of the distribution or one tail of the distribution. So that means in first problem, we are looking whether the test statistic T assumes a value only on the higher side, and in the next problem, when we are testing theta equals to theta naught against theta less than theta naught, we are seeing whether the test statistic T is assuming a value which is on the lesser side. So either on the higher side or on the lower side. We are not considering both the sides. So that is why this is called one-sided test. Now we come to two-sided tests. We consider the testing problem theta equals to theta naught against theta not equal to theta naught. The interpretations are same. To be specific, let us consider the previous problem that we dealt with, p equals to half against p not equal to half. In this situation, when we are going to reject h naught, when the number of heads obtained out of 10 tosses is large as well as when they are small. So that means here we shall be looking for the values of the test statistic which are on either side or either tail of the distribution. So these type of tests are known as two-sided tests. Now in both one-sided and two-sided tests, we are looking for such values of t either on one side or on both the sides for which we are going to reject the null hypothesis. Now these values of t for which we are going to reject the null hypothesis are known as significant values of the test statistic. That means those values which belong to the critical region. You can see in the diagram that in both sided tests, we look for a value of t on either side or both sides or both tail of a distribution. This is why these are called both sided tests or two-tailed tests. Then we come to a very important thing, p-value. Let t be a test statistic, capital T, and small t be its value for a set of sample observations. And our problem is to test h naught, the null hypothesis, against an alternative h1. Now for a one-sided test, or to be specific for a right-sided test, that means such tests, theta equals to theta naught against theta greater than theta naught, the p-value is defined as probability capital T greater than equal to small t given h naught. This is the p-value of the test for a right-sided test. That means probability that capital T, the random variable, the statistic, will exceed the observed value of the statistic, that is small t. For a left-sided test, it is probability that t less than equal to small t given h naught. This is the p-value of the test for a left-sided test. For a both-sided test, it is a bit complicated. 2 into minimum of two quantities. The first quantity is probability t greater than equal to small t given h naught, and the second quantity is probability t less than equal to small t given h naught. Since it's a both-sided test, we cannot think of the value of the higher side or the values only on the lower side. We have to think of values on both the sides, and we'll take the minimum of these two. And these will be denoted by small p. We reject h naught when small p is less than alpha, where alpha is the level of significance of the test. So again, I am repeating, we will calculate the p-value. This is one way of performing the test of the hypothesis. We will calculate the p-value and we will simply compare it with the level of significance. There is another way, that is the classical way, that is we look at the value of the test statistic and compare it with the tabulated value. If the test statistic follows some well-known distributions like normal, chi-square, TF, we can go for tabulated value. But if the test statistic does not follow common distribution, there may be situations where the test statistic will have a mixed distribution, a mixture of discrete and continuous distributions. In this case, we have to resort to p-values. There are several applications of testing of hypothesis. We will discuss more applications in the next lecture. But here we will point out one very real-life example. Suppose it is observed that the average recovery for a knee surgery patient is 8 weeks. A physician believes that after successful knee surgery, if the patient goes for a physical therapy twice a week rather than thrice a week, the recovery will be longer. Conduct the hypothesis of this statement. So you can think of this question. So that means whether in which method the recovery will be faster. So that is the testing problem. So we can construct the hypothesis. We can think of another example. David is a 10-year-old who finishes a 25-year freestyle in the mean time of 16.43 seconds. David's father bought goggles for his son, believing that it would help him to reduce the time. He then recorded a total of 15 25-year freestyle for David, and the average time came out to be 16 seconds. Here also we can conduct a hypothesis by using testing of hypothesis problems. There is a more real-life example. A tire company claims that a segment of tires have a running life of 50,000 miles before they need to be replaced. And previous studies show a standard deviation of 8,000 miles. After surveying a total of 28 tires, the mean runtime came out to be 46,500 miles with a standard deviation of 9,800 miles. Is the claim made by the tire company consistent with the given data? We can conduct hypothesis testing by the theory that we have learned so far. So these are all real life examples that we have to deal with. And we will see in our subsequent lectures how we can deal with these real life examples. Thank you.